Hello, Physics 2B, and welcome to Week 5A, Tuesday, March 2nd. Today, we got just a few particulars to go over first. I've been trying to catch up on grading, so just a couple more assignments and I should be all caught up. To make it so I don't get further behind, let's consider today's warm-up. The warm-up for today, I want you to do after the lecture, and hopefully that's why you're watching the lecture now, so you're ready for it. But it involves a circuit. And it involves a circuit, and I'm going to go over the particulars of how to break down a circuit very similar to the one on the warm-up today. Something that makes today's warm-up different is that it is using the respondus lockdown. Okay. So why am I using lockdown browser now? We haven't done that for any of our previous warm-ups. Why start it now? I'm doing this for practice. Now, the warm-up itself isn't practice. Well, all of the warm-ups are practice, but it's still worth points. I'm doing the lockdown browser now because we do have the exam coming up in just over a week. Okay, a week and 2 days. And that exam will be using the lockdown browser. So I want students to get a little bit of practice using the lockdown browser now. I've set up the warm-up so that you can actually get all the information you need ready before you even enter the lockdown browser. The circuit is visible beforehand. You can find the currents on your own, find the voltages on your own, find the power outputs on your own, and then have all that information ready so that you go in, you can just copy down the information that you've already deduced and calculated. Big things I've been finding out is some students just have a little bit of trouble with the lockdown browser the first time. Maybe you've used it in a different course already, maybe you haven't. If you do have trouble with the lockdown browser, it does involve having an extension connected correctly. So that's a program that needs to be downloaded correctly and installed correctly. Sometimes people have it installed correctly and just a couple of the settings aren't quite right. And a restart of the computer solves that over 90% of the time. That other less than 10% of the time, send me an email and I'll find out what's up. This is also a good time for me to find out if there's any issues you are having with the lockdown browser. So please let me know if there's any issues. Otherwise, I'm hoping the warm-up will go well. Okay. Next, the discussion today. The discussion is also helping to get you prepared for the midterm already. It's saying we're in the second week of going over circuitry things, and at this time people start to forget all the things that we've been going over beforehand. So the warm-up is getting you to think about all that stuff that was in the PDF book. What questions do you have? What considerations are you worried about? And getting a system of saying what you're having trouble with, and maybe helping others in the class with issues they're having if you've got some answers. Okay. So it's a version of test prep. It's a version of study to get you ready for the exam in just over a week. With that in mind, how much more material are we going to cover if we've got an exam this week? These slides are the last of it for the unit. Okay. We've got these slides left to go. We've already covered these slides. And these slides that we have left to go, I will be covering these ones today. and the other one's Thursday. Okay, so I'm going to be going slow and steady through these so that I can reiterate and do examples right on the fly. We'll be doing a lot with resistors here, focusing especially on what it means for resistors to be in series and parallel. And it's a lot like what we did with capacitors, except for some of the rules are slightly different because capacitors and resistors act differently in circuits. Okay. Anything else before moving forward? As always, if you have a backlog of assignments that you just haven't completed, do consider getting at least partial credit on those. I'll give you a partial credit for the late assignments. So we're just approaching the first exam, so I'm just trying to remind people we're still at a point of growth in the semester. So hopefully we can take advantage of it. Speaking of taking advantage of it, that was 6.5 minutes. Let's see what we can do with the rest of the hour or so of this. Right here, we're looking at a circuit that seems to have a single resistor in it. But it also seems to have two resistors in it. There's one resistor on the circuit, that's this guy. Same as this guy. And there's another resistor in the circuit here. And that's what's called an internal resistance. Batteries have two aspects to them. We've got the internal resistance to them and the EMF of them. The EMF is the way I've been treating batteries for most of the time, and I will continue most of the time to just be referring to the EMF as the entire battery. But many times we do have to think, oh, batteries are made of stuff. Being made of stuff, that means that that stuff has some resistance. Therefore, batteries have some innate resistance built into them. And when a circuit is being created, sometimes that's important. And other times it's trivial and not a need. The business part of the battery, the EMF, stands for the electromotive force. Now you'd be saying, I thought you just said that it was a voltage. Why are you calling it a force? That's because it's the part of the battery that does the pushing. And that voltage difference is directly related to the electric force. Remember that the electric force is equal to the charge being pushed multiplied by the electric field, where that electric field is also equal to the negative of the difference in voltage over some distance. So it really is the difference in voltage created by the battery that causes charges to be pushed around, that causes electrons to move. Okay. So when you see that in the book, try not to be too weary of why it reads like that. When we have both of these resistors to consider, we can think of them as being in series. So in order to handle a situation like this, we need to know the general case of how do we handle resistors in series and how do we handle resistors in parallel. Series first. For resistors in series, first I should draw out a representative circuit. And instead of the 2 resistor one that we have up here, let's make it a 3 resistor circuit. where you got a battery, where we're just considering the EMF from the battery, that pushing delta V. And there's a resistor, there's another resistor, and there's a third resistor, R1, R2, and R3. We can see that they're in series because there's a continuous line that runs through all three of them without a junction breaking off current in some direction. The current through each of them is the same. And we'll deal with that later on. First, I want to look at this as if it were a water slide, and I want to consider the loop law for it. We've got that EMF provided by the battery. Then each of those resistors is its own different slide for this water park, so that the EMF provided is the same as the voltage 1, voltage 2, and voltage 3 all added together, exactly as we're seeing right here. I'm going to take that equation from Kirchhoff's loop law, and I'm going to apply Ohm's law to it. Remember that Ohm's law is that the voltage across a resistor is equal to the current through the resistor multiplied by the resistance of the resistor. For each of these individuals, I will replace the voltage by current times the resistance. That's exactly what is done here. On the other side, I want to be a little bit more careful with the language of what's being done here. Because when I'm talking about the R equivalent, I'm not talking about the resistance of the battery. I'm talking about the resistance of the circuit. So I'm visualizing for this equivalency being the battery that's doing the pushing, EMF, has some equivalent resistor in the circuit. That's boiling all three of those resistors down to a single equivalent resistor. In this situation, that battery is pushing current through the circuit, so that the voltage across this guy is the same as the voltage provided by the EMF, and it is also equal to the current provided by the EMF multiplied by the resistance of the total circuit, the equivalent resistance of the circuit. And there we have it. Just want to be a little more careful about the language on that one. A couple more steps to go. Next, I'm going to use Kirchhoff's junction law, which I mentioned earlier with this blue line over here, where I said that all of these are in series, and since they're all in series, they all have the same current. Not just the resistors, but the battery that's supplying that current as well. So the current provided by the battery, current 1, current 2, current 3, they're all the same current. And what I'm going to do with that information is I'm going to go up to the above equation, and I'm going to divide the entire thing by the current that's the same for all of them. That will cancel out all of these capital I's, all of these currents in the circuit, leaving me with, well, this looks a little censored down here. Let's write it up here. We end up that the resistance in series, the equivalent resistance in series, is equal to the resistance 1 plus the resistance 2 plus the resistance 3. And if we had more, there'd be more. This might not be what you were expecting, because this is exactly the opposite of what we got for capacitors. Okay. When we were talking about things that were in series, and more specifically, when we were talking about capacitors. I'll do that in red. Those capacitors in series, we had to do the awkward inverse equation. 1 over capacitance in series is equal to 1 over C1 plus 1 over C2 plus 1 over C3, etc. But now we've got the resistance equations for the resistors. And for resistors in series, we ended up with resistance in series is equal to, and a simple addition of the individual resistors. Why are we getting this opposite result? The Kirchhoff laws are the same, but the voltage equations are different. Remember that the voltage equation for a capacitor is the charge on the capacitor divided by the capacitance. That's specific to capacitors. Whereas the voltage across a resistor is equal to the current through a resistor multiplied by the resistance of the resistor. That is our big distinction. Whereas here, capacitance is in the denominator. Over here, resistance is in the numerator for their respective voltage equations. That's how they're opposite, and that's why their equations are opposite as well. The series equations are different, but like I said, the Kirchhoff equations are the same. Okay? So whenever we have elements that are in series, it doesn't matter if they're capacitors, resistors, batteries, inductors, any elements in series, due to the Kirchhoff junction law, if you have no junctions to split off any of the current, then all the currents and charges are the same. So all charges are the same, and all of the currents are the same. And that is specific to series. Let's see if we get this result for the resistance equation again. Do we get this result for the resistance equation again if we go about it a different way? What if we use the resistor design equation? That same one that was in the simulation last week. That's the resistance is equal to the resistivity multiplied by the length of the resistor divided by the area of the resistor. Well, let's take a look at this setup in series. When I draw them in series, I'm going to slam each of the resistors together so that there's a first resistor, there's a second resistor, and there's a third resistor, all in series with each other. Looking at this thing, it seems to have some total length. And that total length will be equal to L1 plus L2 plus L3. As such, there's our starting equation. L total is equal to L1 plus L2 plus L3. And I did not forget about the addition signs. At this point, I want it to look more like the resistor design equation. I look at the resistor design equation up here, and I see that it does have the length in it, but it's also multiplied by the resistivity and divided by the area. So that is what I am going to do. I'm going to multiply the whole thing by the resistivity and divide it by the area. when I distribute that through, I end up with resistivity times length total divided by the area. I'm going to get my symbols in here right off the bat. Then go through it color by color. Red, resistivity, L1 over the area. Blue, resistivity, length 2 divided by the area. And green, resistivity, L3 divided by the area. Each and every one of these looks like the resistor design equation. It just has some subscript on the length. So this first one is the total resistance. For what situation? Series. The red one is the resistance for the first one. The blue term is the resistance of the second resistor. And the green one is the resistance for the third resistor. And this could have gone on more and more for more resistors in series, had that been prudent to include them. This result here is the same result as we got here. I like it when I get the same result two different ways. It's a good sign. Let's try this again. But this time, instead of doing a resistors in series situation, we're going to do resistors in parallel. Resistors in parallel. Be helpful to have a circuit here for reference that has a battery in it, our first resistor, our second resistor, and our third resistor. Okay. In fact, I'm going to be needing something like this later on as well, so I'm going to copy and paste it over. Not the prettiest one, but it'll be helpful for later. There we go. When I look at this thing, I'm going to start with Kirchhoff's junction law. What junction? My junction is actually going to be this entire grouping of wire. That's my junction. There's current going into that junction, and there's current going out of that junction. The current going into that junction is going to be the current from the battery, the EMF. Next, we're going to have the current coming out of there and going through resistor 1. We're going to have the current going through resistor 2. And we're going to have the current going through resistor 3. In equals out. We've got the current coming in from the EMF, and then my colorful mix of them coming out. 1, 2, and 3. Next, we're going to follow up the Kirchhoff law with an Ohm's law. And you'll notice that I hope over and over and over in the examples today. I use a Kirchhoff law, then I use an Ohm's law. I use a Kirchhoff law, then I use a power equation. I rarely will I use multiple Kirchhoff rules in a row, unless I'm double checking a result. How am I going to use Ohm's law? There's no voltage in this equation, but there is current. So I'm going to solve it for current. Current is equal to voltage divided by resistance. So I1 becomes V1 over R1. I2 becomes V2 over R2. I3 becomes V3 over R3. And for the same semantic reasons as last time, the voltage provided by the battery divided by the equivalent resistance of the entire circuit, not of the battery, but of the circuit, is equal to the current provided by the battery. Because for this jump from there to there, I'm visualizing the circuit being simplified all the way down to a single equivalent resistor, the EMF pushing some current through the circuit. I'm going to simplify this. And I'm going to simplify this using Kirchhoff's loop law. Kirchhoff's loop law, we'll be looking at each of these. That's a loop. Those two elements have the same voltage. This is a loop. Those two elements have the same voltage. This is a loop. This element and this element have the same voltage. And via the transitive property of equivalence, each of these resistors and the battery all have the same voltage. Therefore, VEMF equals V1 equals V2 equals V3 equals just some generic V. So I'm going to take the entire equation above and divide all that voltage out of there. So it's all the same voltage. V, 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 and V. What am I left with? This. A nice 1/, equation that is specific to resistors in parallel. Again, this is the opposite of what it is for capacitors. Now that we're looking at in parallel, the capacitor equation for parallel is adding them up. C1 plus C2 plus C3. But for resistors, we got our inverse equation. And this reason for them being opposite again is the same as it was earlier about the voltage equations being different in terms of 1/, capacitance versus proportional to capacitance. Even though the capacitor and resistor equations do end up being opposites, there are things about them that are the same in parallel, such as the Kirchhoff rules. Kirchhoff rules are universal. Previously, we looked at the junction law telling us that all of the currents are the same in series and all of the charges are the same in series. Well, in parallel, we used the Kirchhoff's loop law to say that all the voltages are the same, specific to in parallel. All voltage differences are the same. Just like we said right here. Let's get this result again. We're going to get this result again with this circuit and with the resistor design equation. I need to redraw this circuit in a way that slams all the resistors together. When I do that, I get the battery. And then resistor 1 is here. Resistor 2 is slammed up right next to it. And resistor 3 is slammed up right next to that one. What's adding up here is the amount of area, the total amount of area that the current can flow through. In that way, the total area is going to be equal to three things added together. Area 1 plus area 2 plus area 3. I would like to use the resistor design equation at this point, but it doesn't look quite right, because these are all areas in the numerator. In the resistor design equation, the area is in the denominator. So I'm going to rewrite this as 1 over the resistance is equal to the area divided by the resistivity and the length. So for each of these terms, I'm going to divide them by the resistivity and the length, which gives me area total over resistivity and length. There's going to be equal sign, there's going to be a pair of addition signs. Red term, area 1 divided by resistivity and length. Area 2 divided by resistivity and length. And area 3 divided by resistivity and length. All of these look like the 1 over resistance, not the normal version, but the inverted way. So each of them is an inverted resistance. 1 over the total resistance, that's the total resistance in parallel. 1 over resistance 1, 1 over resistance 2, and 1 over resistance 3. Exactly the way we expected it to end up, based off of this derivation on the left. Same result, two different derivations. Always a good sign. Next, let's get these things on the workforce. Let's zoom in. Let's take a look at a combo circuit and see if we can identify. Let's see if we can break this thing down. Right off the bat, we have the 8 and the 4 on the left. They have a common line between them. Therefore, they're in series. Since they're resistors in series, we add them together. 8 plus 4 gives us 12 ohms. Exactly what we get done here. Next. This other one has a common junction before and a common junction after. Two common junctions, that is parallel. Being in parallel, we get to use the 1 over equation. 1 over the resistance in parallel is equal to 1 over 6 plus 1 over 3. And this is my favorite fraction to add together. Yep, I have a favorite fraction to add together. It's a food-based reason. Because if you cut up a pie, like so, this big chunk on the right, that is half the pie. This next largest chunk is a third of the pie, and this last sliver of it is 1/6 of a pie. Totally reasonable way to slice a pie if I'm getting the half on the right. Therefore, we can see that 1/3 plus 1/6 is the same as 1/2. That's not the last step, though. RP is therefore equal to 2 ohms, which is what we get down below. Before I break down the part down below, I want to just tell you guys that Pi Day is coming up. Pi Day being March the 14th. Unfortunately, it's happening on a Sunday. Okay. So, on Monday, I will be stuffed with pie, and by Tuesday, I should be good again. Usually, I celebrate this one by eating some quiches in the morning, some pot pies midday, some pizza at night, and some fruit pies for dessert. It makes for a really nice day. It's also Einstein's birthday. So, lots of stuff to celebrate for Pi Day coming up shortly. The weekend after the exam, so you can rest your brain for a little bit then and enjoy some pie. Or whatever it is you're so inclined to do. Next breakdown. Our next breakdown is with these two resistors. We've got a 12 ohm resistor here, a 2 ohm resistor, and they have a common line between them. With the common line between them, that means they are in series. Being in series, we can say that R series is equal to R1 plus R2, which is going to be 12 ohms plus 2 ohms, which is 14 ohms. And there we have it. We've broken down this circuit into a singular equivalent resistor for the circuit. Let's get some more practice with this. The more practice we do with this is going to be centered on building up those tables like we did for capacitors. The circuit in question is going to be powered by an 11 volt battery. In a little bit it'll be clear why I'm using an 11 volt battery. It makes the math easier. And a 10 ohm resistor, a 20 ohm resistor, and a 30 ohm resistor. Note the shape I'm doing for the resistors. It's a squiggly line. Okay, that's kind of meant to be reminiscent of the random walk that the resistors have to take. The random walk that the electrons have to take through the resistor. So that you can visualize that being distinct from a capacitor in that way. Let's break this thing down. The first thing I'm noticing, the 20 and the 30. The 20 and the 30 have a common node beforehand, and they have a common node afterwards. As such, they're definitely in parallel. In parallel, 1 over RP is equal to 1 over 20 plus 1 over 30. Not quite as interesting as the previous fraction, but it'll do. These have a common denominator of 60, so that the common denominator for 1/20th would be 3/60ths, and to get 30 up to 60, that would be 2/60ths, which combine to 5/60ths, or 1/12th. Don't forget to flip the result. And for the resistance in parallel is equal to 12 ohms. Take that result, redraw the circuit. These redraws are really important. It really helps show the sequencing of what's happening, how you're breaking it down, and by looking at everything that included and suddenly not being included, we can keep track of all the elements, hopefully. Such as this red one is 10 ohms, and the P one, the pink one, is the 12 ohms. These two are in series. I can see they're in series because a single line can go straight through them, no junction. Being in series, resistance in series is equal to resistance 1 plus resistance 2, which is equal to 10 ohms plus 12 ohms, which gives us 22 ohms. And then we reduce this entire circuit down to one battery and one resistor. That one resistor is a 22 ohm resistor. That's our equivalent resistance for the circuit. Let's put all this into a table. Our table is going to include resistors 1, 2, 3, and the battery. For each of them, we're considering some resistance. That includes the 10 ohm, the 20 ohm, the 30 ohm, and the equivalent resistance of 22 ohms. Next column. The other information we know something about is voltage. The voltage, we know it for the battery. That is an 11 volt battery. We do not know any of the other voltages yet. Next is current. The current, we don't know yet. And then the power. The power for each of them, we do not know yet. But we can calculate the current. Looking at the current, thanks to Ohm's law, which is V is equal to IR, we can also say that the current is equal to the voltage divided by the resistance. So down here, the current would be the voltage divided by the resistance, which would be equal to 11 divided by 22, which is equal to 1/2. In other words, 0.5 amps. Make that 0.5 amps. Then for the power equation. The power equation, I'm going to be over and over and over using power is equal to current multiplied by voltage. Now I could use power is equal to current squared multiplied by resistance instead. Rarely am I going to use that. I would use that when I, 1, don't know the voltage, and 2, maybe the elements are in series. So I know the current of one, therefore I know the current of the other ones too. So that way I can use a little bit of logic to figure out the current without doing additional calculations like finding the voltage. The other power equation, voltage squared divided by resistance. I would use this one if I had a similar situation where it's a bunch of parallel elements, where I know the voltage across one of them, therefore I know the voltage across all of them. And I don't want to calculate the current, so I just use this equation there instead. But in this case, when in doubt, power equals current times voltage will be useful just as easier. And it's easier because it's a single multiplication. So here we are going to have current of 0.5 multiplied by voltage of 11, and that gives us a power of 5.5 watts. There you go. What can we do with this? We finished the resistor column. We finished the battery row. Now we need to go back and figure out, does any element have anything similar to the battery? And I'm going to go all the way back to the original equation on this one. The original circuit on this one. And when I do so, I notice something here. I see that the battery is in series with the first resistor. Okay. They aren't both resistors, so I can't use the resistor equations. But since they are in series, I can use that universal equation and find out that any element that is in series has the same current. As such, I'm going to say, okay, current of 1 and the current of the battery are the same, 0.5 amps. All right, it's looking better already. I can now finish the row. The voltage will be equal to the current of 0.5 divided by the resistance of 10, which gives me 5 volts. The power will be equal to the current of 0.5 amps multiplied by the voltage of 5 volts, which gives me 2.5 watts. 2 rows done, 2 more rows to go. At this point, I'm going to redraw the circuit. And I'm going to redraw the circuit because I've used series, I've used Ohm's law, now I'm going to go back to a Kirchhoff law. Like I said, that pattern happens sometimes. And it's easier for me to see loops if I draw that water slide. So we got our power supply. That power supply is a 11 volt power supply, followed by resistor 1. Resistor 1 has a drop of 5 volts. And then it's followed by the next two. The next two being resistor 2 and also resistor 3. Wiggly. When I consider the loop, this big loop that's on the left, I can say that 11 is equal to 5 plus whatever the blue is. Therefore, the voltage in blue must be 6 volts. Then I'm going to draw another loop. First I'm going to label. Always label 6 volts. Now the green. For the green, I'm going to draw a pink loop. That's going to be this loop. There's only 2 elements in that loop because these 2 elements are in parallel with each other. Therefore, this drop here is also 6 volts. Something that happens to 2 elements in parallel all the time. This is working out nicely. Moving on forward. Blue. For the current, that's going to be the voltage divided by the resistance, which is 6 divided by 20, which is the same as 3 divided by 10, which is 0.3 amps. Multiplying those voltage and currents gives me current of 0.3 amps multiplied by a voltage of 6 gives me 1.8 watts. Last row. V over R will be equal to voltage of 6 volts divided by a resistance of 30 ohms. I know in my head that 6 times 5 is 30, so this is 1/5. In other words, this is 0.2 amps. I want to slow down here for a moment, though. I want to slow down here and remember something I said about junctions earlier. I'm going to consider this junction right here. Okay, should probably do this in a different color since pink's already used and orange is already used. Let's go with purple. For this purple junction, we have a red current going in. That red current is 0.5 amps. We have a blue current out. That is 0.3 amps. And we have a green current going out. And that current is 0.2 amps. The good thing about that is 0.3 plus 0.2 is 0.5. Current in does equal the current out. Nice little check that things worked out correctly. Looking good. That deserves a smiley face. We're going to have one more calculation and one more check on that calculation. Green row, I times V will be equal to 0.2 times 6 gives me 1.2 watts. In this situation, I want to consider, is energy conserved? Does the energy in equal the energy out? Or in other words, does the power in equal the power out? Well, consider right down here. Considering right down here, we've got that the power out is going to be equal to 2.5 plus 1.8 plus 1.2, which is the same as 2.5 plus 3.0, which gives us 5.5 watts for the power in, exactly as we expected. Another confirmation, another good thing. All right. This is the same type of procedural as we did for capacitors, just slightly different equations and being able to break down a few more things. Okay. If you do a breakdown like this for the equation that's given to you in the preparation for the warm-up screen, you're going to be more than ready to do the warm-up as soon as you enter the lockdown browser. Okay, so do this breakdown before entering the lockdown. Good stuff. Additional considerations. Well, let's consider specialty circuits. I'm going to consider this specialty circuit where we've got a battery, we've got a resistor here, we've got a resistor here, we've got a resistor here, we've got another resistor here, and I'm going to forget the resistor there, but I will put some here and here. Okay. What I did here is I created a short circuit. The short circuit is this right here. What makes it a short circuit? A short circuit is a type of a shortcut with no resistance. And that's effectively what a wire is. A wire is a very good conductor, and that very good conductor has a very low resistance. And for these purposes, no resistance. Why is that important? It's because electrons are lazy. You heard it here first. Electrons are lazy. Electrons, on average, take, that's not how you spell take the path of least resistance. On average. Okay. But if there's zero resistance, that means that all of the current will go through there. So whatever current goes through here completely goes through here. Meaning that the current for this one will be zero, and the current for that one will be zero as well. If those currents are zero, then their voltages are zero too. Remember that the voltage across a resistor is equal to the current multiplied by the resistance. Therefore, their voltages will be zero, and their voltages will be zero. That's a problem. Because what this short effectively did is it took these two resistors and it kicked them out of the circuit. These shortcuts happen. A short occurs when a resistanceless wire is placed across other elements in parallel. And that's exactly what happened. Okay, so beware of that. Okay. Now, the other elements still get current. There is still current coming from the battery. There's still current being divvied up in these locations and divvied up in these locations. But the current through this resistor is the same as the current out through the short circuit and back the other way, completely omitting those from the circuit. I see this happen in lab a bunch. Okay. I see this happen in lab where students are setting up a circuit and they're like, okay, I got everything connected. And they have this breadboard, this grouping of circuits where everything's already connected like that. And you got another thing connected right here. And they have another resistor available over here. And what I've seen far too many times is they'll take their battery and they'll say, here's parallel. Thinking that they had to do a special wire across the resistor, when really what they did is they end up with a result that doesn't have anything in the circuit except for loops and no resistance. This is not good for power supplies. It maxes out how much current they can safely output. So what negligible resistance the wires has, that's the resistance of the circuit. Instead, do not short circuit your resistors. It causes problems in the labs. Okay. With our time left, let's go back to this circuit and do another breakdown. But this time, let's not have a short circuit in it. Okay? So basically the same circuit, no shorts. So far, so good. No shorts. Kind of like working for a company that wants you to look a little more fashionable. No shorts. I've never been told not to wear shorts. But I looked at my legs while wearing shorts and I was like, it just doesn't look quite right. We'll save that for a fun day. All right. There's our circuit. I'm going to identify all of the elements that are in series or parallel with each other. In fact, I see two sets of resistors that are in parallel. Can you see them? Firstly, we have R2 and 3. Those are in parallel with each other. So we can say that in parallel, 1 over R2, 3 will be equal to 1 over R2 plus 1 over R3, and calculate accordingly. Over on the right, 5 and 6 are also in parallel. As such, 1 over R5, 6 will be equal to 1 over R5 plus 1 over R6. We'll take that and we'll simplify the circuit. We got our battery. We've got resistor 1. And then we've got these two resistors combined together. Then we've got R4. And we've got 5 and 6 combined together. We got 1, 4, 2, 3, and 5, 6. I now see two that are in series with each other. The two that I see in series with each other are these two. One wire, no junction, must be in series. That resistance in series, I'm going to use S for this, is going to be equal to resistor 4 plus resistor 5, 6, which we just could get from that calculation. And there we have it. Let's do another redraw. Gotta save a little time on this redraw. Boom. And draw this circuit like so. I did this in the previous class, and a student was a little weary of it. How is that the same as the other one? Well, I checked, and he said that he wouldn't have known the difference had I just drawn it like this. And I want you to be able to see that these two drawings are the same circuit. All that I changed was I used a short wire here, and over here I used a long wire. Same circuit. Okay. As such, on the left, there's a common wire before and a common wire after. Those are in parallel. Drawing on the right, common wire before, common wire after. Still in parallel. That parallel, 1 over R parallel, is equal to 1 over RS plus 1 over R23. And I'm going to do another redraw. We got resistor 1 there, followed by resistor parallel from the above calculation. And these can be combined into a singular resistor. The equivalent resistance of the entire circuit, which will be resistance 1 plus resistance P, which I could have gotten from there to there. That's the breakdown of the circuit. Important things to be able to do: identify series and parallel. Okay, that's the big thing. A big safety thing is avoid shorts. Okay, do not try to avoid shorting elements in your circuit. It's really dangerous if you're using a high voltage, high current power supply. I got a buddy that has working on his home. He turned off all the lights and started working on the electronics in the wall. Unfortunately, one of the light switches for one of the panels was in the other room, and that one was still on. So he took his wires and he was about to snip one of the wires. It was a live wire, and suddenly there was enough current flowing through those little snips to blast a hole in the snips. They were done. Like there was a hole that looked like a crater had been taken out of the snips. Completely useless. Okay? He did fine. He was fine. They're well insulated handles, so he was safe. I screamed in a very high voice, so it was a good time. There's a video online of someone shorting a car battery with I think it's a screwdriver, and they're doing it on purpose. They actually have a whole setup done, and they're saying, hey, what happens if you short a car battery with one of these metallic tools? And enough of a voltage difference is there that an arc is created from the tip of the screwdriver to the second lead that's not even touched yet. Okay, sparks fly, but it was in a controlled situation, and it looks pretty cool. Not something you want to do. It gets all of the energy out of your battery, so that battery can't be used anymore, and it ruins your screwdriver, so that's not good. And if you have your safety protocols off, it is possible to have a serious shock occur that can cause serious damage to your heart or brain. Okay? And there's two things that you really want to keep safe: your heart and your brain. The rest can mostly be fixed. Heart and the brain, you need those every second of the day. All right, so that is a breakdown of the circuit. Next class, we'll be looking at this consideration. In this consideration, there's something weird that happens. I got 2 batteries in this circuit and 3 resistors. But none of my resistors are in series with each other. Let's check out 4 and 6. No, there's a battery in the way. 4 and 2. No, there's a junction in the way. All right. What about 6 and 2? No, there's a junction in the way. That junction makes it so that the currents are different. And since the currents are different, it's no longer in series. What about parallel? Here's a common wire between 6 and 2, but the other one's interrupted by a battery. Therefore, not parallel. 4. Well, you can't get from 4 to 6 at all, so those can't be in parallel. And from 4 to 2, there's one side, and the other side's interrupted by a battery. So, no series, no parallel. What can you do when you can't break a circuit down into series and parallel elements? You use what is universal. You use the Kirchhoff laws. So on Thursday, I'm going to go through this circuit, and I'm going to go through a few more examples, and I'm going to show how you can use Kirchhoff's loop laws and Kirchhoff junction laws to determine the voltage differences across each element and the current through each resistor. Okay. It'll be very mathematically intensive, so it's very helpful if you have a TI graphing calculator available, because then I can walk you through how to use a TI graphing calculator to do all the math for you in the end. Or I'll also show you how to do the algebra. After that, I'll go over RC circuits for a little bit, and that'll be it. Unlike pretty much everything else this semester, I am not going to do a derivation for this one. And I'm not doing a derivation for this one because the only derivations I have available for where the equations come from are calculus based. Therefore, we will be doing a qualitative understanding about it, and we're going to be using those qualitative understandings to relate what happens when we have a mixture of elements, capacitors, and resistors in circuits. Specifically these 2 situations. A charged capacitor with a resistor, and a battery, a discharged capacitor, and a resistor, all in the circuit together. That's what you have to look forward to on Thursday. Good luck with the warm-up. Good luck getting started on the preparations for the first exam. And if you have any questions, please let me know, and I'll get back to you as quickly as possible. Thank you. Have a nice day.